Okay, let me share my screen again. Just a minute. Close the file also. Give me one more minute. Okay, so everything fine? You can see the screen? You can hear me? Somebody? Hello?
No, sir.
You guys can hear me?
Screen is not visible.
Can you see the slides? Yes?
Yes, sir.
Okay,
Yes, sir.
okay, good. All right, so we're talking about erosion, then etching. So like I said, etching is more like a chemical process. And you know that natural system, nature also has a lot of acid here and there in the environment. So an example is being given here, like you can etch away silicate rocks, okay? So again, silicate means basically silica by carbonic acid from the environment, okay? So that is a process of etching. So then another process is called hydrolysis. So hydrolysis basically means breaking up of water. Okay, a typical example when we make oxygen and hydrogen from water, we use some electrical connections and put some electrodes and we can separate it out water, right? So that is called hydrolysis. Hydro means water, lysis means to break up. So we can have some decomposition of the organic or inorganic material available in nature through hydrolysis processes, and the decomposition results in the formation of nanomaterials or nanoparticles. Volcanic activity, I already mentioned before that this is the way that lot of small nanoparticles end up in the atmosphere. Okay? Typically fly ash, right? So whatever particles are formed through natural volcanic activity, they remain suspended in the air because they're thrown up with a high force into the atmosphere. Okay, so volcanic byproducts contribute to the formation of clays like Montmorillonite. That's an example. Okay, it's a nanostructured material. Now this is I picked up this table from a book where I had written a part of that book, and I'll share you some information as class notes from that particular book, right? I'm not supposed to distribute the book because it's quite an expensive book and the publishers will be upset if I keep on distributing, but I will share some contents with you all right? Forest and brush fires, okay? So there also, through combustion, when we have something is burning up, mostly carbon is being released, okay?
Hello. Hello, sir.
Yes,
Hello.
yeah, tell me.
You are not audible, sir.
I am not audible. How about now? Not clear? Let me see. What is the problem? Well, my microphone shows very clear. Is it happening to everybody?
No, sir.
Some of you can hear me clearly?
Yes, sir.
Okay. So those of you who did not hear me, maybe some issues with your network, okay? Anyway, I will share the slides and I'll also give out some notes for you to read yourself. So try to check out your network. All right, so fire is one way that nature has been, natural fires come up and you have a lot of carbon particles, all right? So amorphous means they are not crystalline. That means the atoms are not arranged in a systematic way. That is called amorphous. Okay, so we get a lot of these particles. Solar activity. That means the radiation coming from the sun. So radiation degradation we call it, of bulk synthetic inorganic and organic materials. Okay, so this is happening. The process is natural. It can be synthetic also. That means the material that has been degraded into nanoparticles can be natural or artificial, but we are using natural solar radiations to make the particles, the nanoparticles. Okay. Another is pressure and temperature, right? So these are directly proportional. The higher the temperature, more will be the pressure. That's what happens in a pressure cooker also, right? So formation of diamond crystallized from pressure and temperature processes applied to bulk material. So diamond, it's a beautiful crystal, transparent, is actually coming from carbon, which is black, right? Diamond is purely carbon. All the atoms are carbon. But then you know that if we talk about carbon, we normally think of it as a black material, right? So that again happens, all right, through temperature and pressure, natural pressure being applied. Of course, natural pressure won't go extremely high, but it can go to high temperatures, high pressures, like the volcanic eruptions. Why does it go to such a height? It throws out, right? Because there's a huge amount of pressure that is being developed inside the Earth's crust, which rise in temperature, and then the Earth cannot hold it further, and it just bursts open, right? So something similar. So we can get diamond crystallites, very, very small crystals, because diamond is crystalline. Okay, that means all the atoms need to be very systematically placed. Otherwise, you won't get diamond. So otherwise, it will be simply amorphous carbon. Right? Biological decomposition. You know what is decomposition, right? It's going to basically natural process of breaking up, breaking smaller and smaller. Okay, you see some animal, dead animal lying there. You go one day, you see almost the new one, the fresh one that has just died. Maybe you go every day, gradually you'll see less and less of the things available there. Okay, it's a simple natural process of decomposition. That means it's breaking up. So decomposition is a process that begins at the bulk, micro or nanoscale level and terminates at the nanomolecular or atomic level, because it goes on breaking, all right, and finally it almost goes to the atomic level. Okay, atomic or molecular. You know what is a molecule? Molecule is basically a few atoms interconnected by some bonds, all right, and they remain together. Okay, so like water has hydrogen and oxygen. Okay, so we talk about a water molecule, right? We don't say water atom, right? So uh, so those molecules have their own identity, they remain together. So that's why when this natural decomposition process continues, it can go down. If the end product is a molecule, it will remain as a molecule, or it is like say only carbon breaking down, then the end product will be a atom of carbon, right? But mostly they remain in the nanometric sizes. That means some remain maybe a few thousand atoms together, they remain there, and those are natural nanoparticles. So biological specimens can end up becoming nanoparticles. Okay, So the biological decomposition is mitigated by bacterial and other life forms. That means bacteria eat up, all right, uh, whatever is there, and then gradually finishes off everything. That's a very typical process we also use. I don't know if you know about how we, purify wastewater. You have any idea? We simply put some bacteria there, and the bacteria has a party on the water that is being thrown out. There's a lot of food stuff there. They keep on eating, and finally, what you get is like clean water. The rest has been eaten up or decomposed. Then there's another process called digestion. Okay, so reduction of bulk biological materials into nanometer and sub-nanometer scale components by the action of acids and hydrolysis. Okay, so it's very similar to what we're talking about, like etching, but the process is slightly different, and we call it as a digestion process. All right, we the typical system that we have also made. This is a natural system, but we have also digesters that we make. Right, you know about the term called digester. So the process is very similar. Basically, action of acids and hydrolysis. The formation of nitrogenous waste is a bottom-up procedure. Okay, so uh, uh, some processes are bottom up, of course. All right, so I'll come to the bottom up processes later after this. All right, so but then top down, the other processes, the other biological materials, except the nitrogenous waste, they are formed by the top down process. Okay, all right, now let's move up to the bottom up process. Okay, so this is a process which we will lay more stress. We'll spend some more time discussing this, because this is something that you can actually do. We all can actually do. We can make nanoparticles. We can make different nanomaterials in the lab itself. Okay, even at home you can do it if you want to, right? So we'll be laying more stress on this. We'll try to understand how this happens. But like I told you, it starts with an atom. Right, this starts with an atom, like this guy building up, using different blocks, right? So it's the same thing. Those blocks are the atoms. So numerous techniques are available, all right, uh, for doing this. Here also, like I said, you all can do it with simple techniques, but also sophisticated techniques are available, definitely, okay, to get very, very consistent particles, the shape, size, everything very nice. So we have complex systems also. So these are some of those systems that make nanoparticles starting from atoms, but in a vapor phase or a gas phase. Okay, that means we have the atoms suspended in a gas. That means we start out with the original material, we convert that to gas, and then we create certain conditions that these atoms moving around in the gas, they start coming together, slowly building up bigger and bigger and bigger till we go to the size we want. All right, maybe a few nanometers, or few tens of nanometers, or few hundreds of nanometers, as far as our requirement. We go to that size and then we stop the process. All right, and we get what we are looking for. So chemical vapor deposition is a very, very common process. All right. So name itself says, first you convert a chemical into a vapor form, and then you deposit it on some substrate where you want the nanoparticles. Okay. So the CVD involves the formation of nanomaterials from gas phase. Okay, usually at elevated temperatures onto a substrate. Right. So the substrate can also act as a catalyst. You know what is a catalyst? Catalyst is something the mere presence of which accelerates certain chemical activity. But the catalyst as such does not change itself. It remains as it is. All right. It's like me walking into somewhere, and the moment I enter, everything changes, but I still remain the same. But everything changes only because I enter. Okay, something like that. So using this process, the chemical vapor deposition, we can get huge variety of nanoparticles a typical or a very popular example is the carbon nanotube. Okay, so carbon nanotube is basically a tube made of carbon in a single layer, right? And if you spread cut out a tube and spread it out, then you get what is called as a graphene, right? So carbon nanotubes are graphene rolled. And what is graphene? Graphene is basically a single layer of carbon atoms. Okay, I'll show you some pictures of graphene later, but this is the only two-dimensional material available. Okay, so graphene is a two-dimensional material because it is a single layer of atoms, right? So it is like a thin sheet of atoms, but it's single layer, and that's why in one dimension you consider it as 0. That means if you say x, y, and z, the z dimension is 0, which is not possible actually. You cannot have a natural system, or it cannot have anything that is two-dimensional surviving in nature. It cannot, it collapses. It has to become three-dimensional, otherwise it won't survive. But graphene survives. I'll tell you why when I show you the figure of graphene later, okay? But this is, remember, if I ask you how carbon nanotubes are made or how graphene is made, you can say one process is chemical vapor deposition. Okay. Another process we call it atomic layer deposition. Here we're depositing materials at the atomic level and we're converting them to nanoparticles. Okay. So ALD is an incredibly precise, okay, we call it sequential surface chemistry layer deposition method. Okay. So basically it's a chemical process to form thin films on conductors, insulators, ceramics, you name it. Any type of substrate you use, you can deposit thin layer of material and the nano size. Okay, so it's a nano thin film, or it's a nano. And I told you, if you remember, we had 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional nanomaterials. So thin film is basically a 2-dimensional nanomaterial because you can spread out in x and y direction, but in z direction it does not spread out. Okay, it is confined. So the layer formed by atomic layer deposition conforms to surface topography. That means it follows the surface roughness. Obviously, because the roughness is supposed in micrometers and your layer that you are depositing is maybe few nanometers. So obviously, it's like covering up a rough surface with a very thin layer, and obviously the thin layer will follow the surface. Okay. So that is what happens in ALD. It follows the surface topography. So alumina layers are generated from hydroxylated silicon substrate, okay, using this chemical. All right. So all these methyl groups, these are methyl, okay, CH3. Don't get frightened with the chemistry. I also is not a great lover of chemistry, but we will keep the chemistry restricted to as much as is needed, right? So don't worry much. So this process, the atomic layer deposition process, can give you thin films with the wide this variation in sizes or the thickness, we call it, even from 1 nanometer. Okay, 1 nanometer is extremely small. All right. If you remember, it is just 10 hydrogen atoms. All right. So that type of thickness we can get using the ALD process. All right. Now another gas phase process is the combustion process. So the formation of silicon nanoparticles from the combustion of silane gas, okay, silicon tetrahalide, okay, is SiH4. So you can use this gas silane, and then you can actually convert that to silicon nanoparticles by removing the hydrogen, right? So there are different techniques of doing it, how to do it, but basically it's a combustion, it's a burning process, right? So the particles you get can be extremely small, even 2 nanometers in diameter, okay? Similarly, you can have alumina particles, aluminium oxide or titanium dioxide. This can be formed by combustion. Okay, so these basically they are metal oxides. Okay, aluminum is a metal. Okay, oxygen, so oxides. titanium oxide, right? So these can be formed by combustion. Then thermolysis, pyrolysis. All right, that means breaking up because of heat or breaking up because of fire. Right. So ignition, one is heating, the other is ignition. Okay, that means you fire it up. So we can get silicon nanoparticles, okay, by the thermal decomposition of silent gas, which we are talking here, right? Silent gas, if we decompose it with heat, excess heat is applied and it breaks up into silicon because the oxygen gets removed from it and it moves out as a gas, right? The bottom-up decomposition of ferrocene to form iron nanoparticles is one of the best example of a bottom-up gas phase fabrication method. Okay, ferrocene is another chemical that contains iron. Like I said, don't get frightened with chemistry, but just remember that whenever there is iron there, and you can actually heat it up or burn it up to remove the other components and keep iron, and then we see that they come together, all these iron atoms, and they form a nanoparticle. Okay. Another process very popular is metal oxide organometallic vapor phase epitaxy method. Okay, so epitaxy is basically naturally forming of a thin layer of oxide on the surface of a material, right? That means if you have an iron rod lying outside, what happens? Gradually it starts rusting, right? You've seen that all your iron pipes, they start rusting. What is rust? It is simply iron oxide. Okay, so what happens automatically due to the exposure to oxygen, gradually the iron at the surface starts oxidation, right? So something very similar. So anything that is there, the surface starts reacting with the existing gases and they form some thin films. Okay, so chemical characteristics of precursor material utilize reactive gas phase organometallic compounds that decompose to form a nanometer scale thin films or nanoparticles. Okay, so this is a very typical process, right? So this much information is enough for you at the moment, right? Then another method is called molecular beam epitaxy. Okay, so this is again is a thin film process. Right? This is done under extreme high condition. You can say high vacuum. That means it has to be in some tube where you use a vacuum pump to suck out the air from inside, and inside the pressure goes extremely low. All right. And using this process, molecular beam epitaxy is able to deposit one atomic layer. That means you can make thin films of single atoms. Right? One atomic layer means the thickness is one atom. Whatever type of atom you are depositing, say gold, silver, whatever. But it is like one layer. You can go using this process of molecular beam epitaxy. Now, these are very commonly used this process when making integrated circuits, okay? Because nano fabrication techniques are very similar to the techniques being adopted for making integrated circuits. Let me tell you why. Because you see, I had worked in a what we call as a microfab, basically means a micro fabrication unit which makes integrated circuits. Okay, I don't know, you've seen picture, I'll show you my picture of myself also. You are totally covered up. All right, you're totally covered up, only your eyes are visible, that through a transparent layer. Is because it's extremely clean. Okay, and to set up a typical fabrication unit, we don't have one in India as yet, because it costs for billions of US dollars, and even to maintain it we need to spend millions every year. It's very expensive. I had worked in that for almost a 1.5 years, and it's very uncomfortable to work. All right, but the thing is that we can use those facilities because they're so expensive. All of a sudden, people started talking about nanotechnology and nanomaterials. Prior to that, it was a what you call a huge transformation came in the field of electronics because of the integrated circuits coming in. Okay, and these integrated circuits, all these setups being made, you cannot now think about making nanoparticles and say, okay, I want to set up another facility for making nanoparticles. How many of us or even big universities or big companies can think of setting another $100 billion to make up a factory for making nanoparticles. There's a huge amount of money, right? So what do? We try to see what existing facilities we have, and we try to see if we can use those facilities to make our nanoparticles, okay? And that's why most of the techniques being adopted for making integrated circuits, the same techniques have already been experimented to make nanoparticles, right? So ion implantation is molecular beam epitaxy is one of those, and normally in integrated circuits we use a lot of gallium arsenide, right? GaAs. Okay, so those processes can go very low. You know, the thin films that we make, it can be even 1 nanometer or just above 1 nanometer in thickness. Okay, this is another indium gallium arsenide. Okay, and we talk about quantum dots. So quantum dots are basically nanoparticles which are 0-dimensional. That means the electron restriction is in all the 3 dimensions. Okay, so it's a typical example of a full-fledged system that that adopts molecular what I mean is what you call as quantum mechanics or quantum physics coming in, right? So ion implantation is another process of doing it. Now ion, what is ion? Ion basically means a charged atom, right? That means an atom is neutral always, you know that, right? That means the number of positive charges at the nucleus is compensated by the number of negative charges on the electrons that are moving around the nucleus, right? You know the structure of an atom. It has protons and neutrons at the nucleus, which are stationary. Neutrons do not have any charge, but basically has the mass. Okay, protons have positive charges, and electrons are moving in elliptical orbits all around, and they have negative charges. And the number of protons and the number of electrons is always the same. That's why atoms as such naturally are neutral. Okay, positive charges neutralized by negative charges, right? Now, if we remove one electron from the system, then what will happen? The system will have a net positive charge now because one negative charge has been removed. So the positive charge that was, this negative charge was neutralizing, that remains free now. It cannot be neutralized, right? So one positive charge automatically comes in. Now when you're talking about, that is called as an ion. Now if you typically think about making ions, the meeting will end in 5 minutes, but I will request you to rejoin, okay? Because there are 2 classes continuously, right? So if after this meeting is over, please do rejoin again, and we will continue after another 5 minutes, okay? After this is cut off.
Okay, sir.
Now let me continue till it cuts off. So ion, you understand now, right? What is an ion? If we can remove 1 or 2 or 3 or whatever number of electrons from an atom, it becomes an ion and it is positively charged. Now, typically, most of the ions are positively charged because it is easier to remove an electron from an atom than a proton. Because the proton, I told you, is in the nucleus at the center of the atom, and it is firmly sitting there, but the electrons are moving around. Okay, so the first thing, that means with lesser amount of energy you can pull out an electron as compared to a proton. All right, so deprotonation is a complex process, but electron removal is slightly easier, and that's why we do some processes that remove certain electrons out, and then we get ions, and these ions are then bombarded on a surface. Okay, at extremely high speed it is thrown on a surface. Okay, so it's you can understand this, right? Something thrown very strongly somewhere, it breaks off parts of it. Say if you're taking a tennis ball and you are hitting it on the wall of your house, okay, the ball comes back to you, right? It doesn't does much damage because the ball is soft. Now think about a iron ball of the same size of your tennis ball and throw at the wall with the same force. The wall might crack up. Some particles or some concrete and paint and brick particles may be thrown out, right, because of the momentum. So that's why instead of throwing electrons at a material, if we throw a atom, we'll do more damage, right? Because the atom is much heavier than an electron, because it has all the protons and the neutrons and everything. Fine. I told you, if you remember, that I used electron beam lithography also, where we are using a beam of energetic electrons to cut out certain patterns. The material that we are cutting out is soft there, and that's why we can use electron beams. But if you want a hard material being cut out, say we have a layer of copper, or we have a layer of maybe silver, gold, and we say we want to strike something and make nanoparticles out of it, throw out nanoparticles, then an electron may not be able to do it because the electron mass is very small. You know what is momentum, right? It's mass into velocity. So a ion moving at the same velocity of an electron will make more damage because the ion has more mass, and the more mass means more momentum. Because velocity is the same for both, then impact made by ion will be much more as compared by an electron. Okay, you understand? So that's what we do. We throw all these ions on a surface and we generate or make nanoparticles. I hope you can visualize the thing. Okay, let me ask you something now. You see, you already understood what is an ion, right? We simply remove a few electrons and an atom becomes an ion. That means it has some charges on it. Fine. Now I said that we were going to throw all these ions on a surface. Why can't we throw atoms? I mean, it's the same, right? Why do we have to go through an additional process of removing some electrons and then throwing? Instead of that, we could have directly thrown the atoms on the particles. Or I mean on the surface. We can directly throw the atoms, right? Why don't we do it? Why do we go for the process of removing electrons before we throw them? Well, definitely there is a necessity, otherwise we won't do it, right? We human beings are anyway lazy. We will do only what is necessary. Why should we do something extra? Well, now think about it. We are saying throwing them. Now, if you throw the ball, you are doing it. You're holding the ball. You are using your own mechanical force generated from your body, and you're throwing it. How do you throw an electron, or how do you throw an atom? Who picks up the atom and who throws it? Think about it. How will you do it? You have a number of atoms maybe sitting there, but you have to provide certain